Well, thanks, Nick, for, can everybody hear? Is the microphone working? Yeah, thanks. For setting the overview of this. That's excellent. And now we're going to plunge into some of the more technical things. But first of all, I'll just make a complaint that I'm talking 29P, actually, just like Pluto isn't a planet, it's actually a giant comet. 29P isn't a comet. It's a giant centaur object that never really has shows a tail at all. So you'll see what I mean when I show you what we found out about this very strange object. It's almost one of a kind. There's almost like nothing like it in the solar system. And that's because it has these unique properties. And amateurs have been at the forefront of exploring what it is that makes it tick and how it behaves. So this is a close-up view taken with a 2-meter telescope. Why it's a centaur is because of where it's located, and it never gets close to the sun. It always sits in an orbit which is set beyond Jupiter. And centaur objects only are characterized in that way because they are between the orbits of Jupiter and Neptune. And this is a case in point. And this is the orbit of 29P. And as you see, it just sits outside there. And the reason it's there is because it probably, almost certainly, was a trans-Neptunian object. And the gravity of Jupiter, of Neptune, Uranus, Saturn has pulled it closer and closer towards the sun, but it's got trapped between Jupiter and Saturn now. And that partly explains why it's very strange. It's also very big. And Damien Peach did a compilation, it's a collage of a number of images, and he's all put it onto one image. And that shows the way in which the coma develops. And Nick kindly showed an animation of that. Now, Mission 29P is a BAA Comet Section initiative that's been going a few years. And the idea is to encourage as many observers as possible to follow it. And it's very easy, actually. You don't have to have a filter, for example. You just need to take a good image with good signal to noise. And each year, I encourage amateurs to do that. And we have, I get thousands of observations. And the principal analysis we do is photometry. We measure the brightness. And here's a list of people who contributed in 2021 to 2022. And you can see top of the list is Jean-François Soulier, who actually built an observatory, a remote one in south of France, and it observes this comet. Here's the light curve, the latest light curve of 29P. I need to explain a little bit about what that is. So it's magnitude here against time. So this is 11 months of time, just finished in June. And what's surprising about this is it has these jumps in brightness. It actually really only ever gets really bright through this process. Again, it's not a comet. It doesn't behave like any other comet. And that's more reason to study it as well. You use the same techniques to study it, but somehow the science of astronomy is unable to explain why it behaves like this. I'll just say, if it didn't have an outburst, and if it was what's called a bare nucleus and had no coma, it would be this brightness, and it would be a straight line. I'll just point out a few things. One is you see that it never gets actually towards the straight line. It stops at about, it's actually twice the brightness, roughly, of the bare nucleus. And that's because there is a background activity which actually is cometary. It's leaking gas and dust into space, and that is a base sort of activity level. But these outbursts are something else. JWST, James Webb Space Telescope, took images of it on February the 20th. I do have copies of the data that came from it, but I can't show it at this official meeting because it's not published. I'm not allowed to, but in the break time, if anyone's interested, we can look at what James Webb found, and it's remarkable. Now, there are a few simple questions we try to answer. One is, how quickly does a nucleus of a comet or an asteroid spin? And so you're always looking for periodicity. Back in 2016, I wrote a paper that was published. I wrote two others ones at the same time, some of which are with other authors. But this is one that looked at the periodicity, and it seemed to show, this is in Minor Planet Center data, that up until 2014, that there was an apparent periodicity of about 57 days. And that's what that plot is. And that's because half of the nucleus was inactive and half was. And so when there was an outburst, it was coming from one side. Another way that seemed to show that this was true is that you could look at an outburst and then wait and see another strong outburst about 2 months later. And it turned out that sometimes it had the same fingerprint. These have been analyzed to exaggerate this pattern that you see. And they're like fingerprints they're actually cryo-eruptions, they're cryovolcanoes. And inevitably, there's not one of them, there's several of them, but they have different fingerprints. And you see this happening after this magical, roughly 57 days. Here's the only other light curve I'll show of it. And again, because this shows that it's the strong outbursts that have the signal of 57 days. And you also notice that you sometimes get another strong outburst very soon after. That's another characteristic we can't yet explain. Now, this shows the results of the last 21 years of data. And what it plots is it's called a rotational phase plot. So this y-axis is based on the assumption that the object is rotating with this time period. And what we found, this is the 2010 to 2014 where we saw this signal, and it was because half of this is like longitude, as the Earth spins and the longitude changes, the Pacific Ocean would show there would be no land for part of the rotation, and as on the nucleus of this object, it too was inactive. But we've continued to observe it, and one thing we discovered in 2014 is that as well as these strong outbursts, it had what I call mini outbursts. And the plots here, they show the intensity of the event, and they're expressed in terms of the equivalent brightness of the nucleus. So if the nucleus is 1, then the intensity of that spot there is around about 200, say. And so it's a way of showing, a factor of 1,000 difference in brightness. Now you can look as well as that, and this, I should say, it confirms the 57-day period, because again, we have a large area, and these mini outbursts were never detected before 2014. It's only the amateurs that have actually demonstrated they actually exist. And if you plot our recent Mission 29P data since 2013, you can see in red are the mini outbursts, and this is a logarithmic plot. So there's a factor of 1,000 difference in intensity between the bottom and the top. And what it shows is that it seems as though mini outbursts are a different physical phenomenon, because they seem to be separated from strong outbursts. And another way of plotting that is to add up all of the outburst activity during the year, normalize it, and then compare each apparition. So this is going back to 2003 again. And it shows, there's the time it takes to orbit the sun, 15 years. And it shows these peaks, these two peaks. And one way of explaining that is that there's an active region in the sort of north temperate zone, and there's an active region in the south temperate zone, and that the poles and the equator are relatively inactive. Right, what else can you do? Well, one thing is, can you catch it in the act of erupting? That's the ultimate. And Jean-Francois, he set up his observatory to do that, and he was successful. But before I show you that, I'll show you happenstance where 9 observatories happened to be observing at the same time this object, and the object went into a mini outburst. And this is the data that we got. So this is the magnitude, and we had 3 observers here. We had Ramon Naves stopped observing just at the point it outburst, so the red squares just finished. And then Jean-Francois took over with his telescope, and then other people, including professionals using the TRAPPIST telescopes. And that shows that this event is very sudden. Again, it's not like an ordinary comet, it happens very quickly. And this is the icing on the cake that Jean-Francois obtained. And actually, Nick was observing when this happened. I've only plotted Jean-Francois, but Nick actually identified that it was coming up around about 14th magnitude at the time. So it was only sort of 30 minutes after it had actually started, and Nick sent out an email, and that meant that a lot of observers followed suit and followed it. And it's possible, because the data is so good, to actually sort of look at it in detail and model what's going on. You know, the way in which you get a cloud of erupted material that obscures the nucleus, and then it will overlap and it will start to grow. And as it grows, it becomes thinner and thinner, and eventually it will let light through, but it doesn't do so until 20 minutes afterwards to this particular event. And this is what it looks like 5 days later. And again, unlike a comet, the brightness of a comet goes as 1 over the r of the distance. So you expect it to get fainter in that proportional manner as you go away from, but as you see, this is a relatively uniform brightness. And that's because it was a single event that erupted and nothing else happened. The vent that produced it sealed over, and all the material expanded into space. And the speed, you can measure the speed at which it expands. And at its fastest, it was going about 165 meters per second. Okay. And if you then look at the light curve, now, one other point to make is you have to measure the brightness with a fixed aperture, a certain aperture. And for this, we normalize it to 5 arcseconds or so. And that means when this expanding cloud goes beyond the aperture, it appears as though the measurement is getting fainter. And that's why it drops down. Now, we had a really intense event, most intense for nearly 40 years, in September 2021. And this is what happened. It had multiple outbursts and it became very bright. And this triggered the professional community to try to follow this up. And they followed it up with SWIFT, the satellite, and subsequently the Hubble Space Telescope. If you actually measure the brightness with different size apertures, remember I said about 5 arcseconds, you get this. But if you increase the size of the aperture, you're going to be measuring, continue to measure it. And so as time goes on, this is 10 arcseconds, 20, 30, 40 arcseconds. And what the surprising discovery is that the actual coma brightness is actually continuing to increase. The intrinsic brightness, and that's never been found before. It's shown so clearly. And there's a paper in preparation, but it's not on that particular subject. It's on the HST observations of it. Quickly, one other thing you can do, I won't explain in detail, but you can measure the brightness with smaller and smaller apertures, so you can get really close into the nucleus. And these are measurements done on images taken with 2-meter telescopes. And it shows the brightness with distance from the nucleus. And you see, typically you get it brighter. So when you have an outburst, so you have a jump up to here. And when I analyzed these various images, I found that the fade was actually taking place in 2 steps. And I couldn't understand why that was. And it was because there were actually 2 outbursts, one about 30 hours after the other one. And one interpretation of this is that part of the ejector falls back because the nucleus is so big, the gravity pulls it back. And that might be what happened there. Now, the HST observations I just mentioned, I actually downloaded the data and I analyzed it and compared it to what Mission 29P had. And there was actually an outburst just less than 12 hours before HST imaged it, and the brightness went up to here. And this was the brightness I measured on the HST images. And then there was a second outburst and so on. Basically, the interesting thing here is that the bare nucleus is actually down here, and this has an excess material close to the nucleus, which was because of that really super outburst that has been the biggest for 40 years. And so at that point in time, there was still material close in orbit around the nucleus. Finally, one thing that we've done recently, and we started thinking about it, was a meeting with Mike Kretlow, a German amateur in Berlin at the EPSC there in 2018. And we were talking, and we said, well, we don't think that the astrometry in the Minor Planet Center of this object is correct, because everybody measures it, observes it after an outburst, and then that shifts the center of sort of the light away from the nucleus. And so what I said, well, we can measure the Fawkes telescope images, and we can get really accurate astrometry of it. And this is what I did. And I built up something like 623 images, used images. And I did all the measurements when there wasn't an outburst, when it was just almost a point of light. And I sent these to the Jet Propulsion Lab and to Paris, and they used the data. And I went over to Canada for a DPS meeting, and I met the guy who actually is responsible for the JPL for doing the orbits. And he said, oh, I need to get this updated. And he updated it, and the Parisian in Paris, they updated it. And what it meant is that the position of the comet was actually out by 1,300 kilometers. If you looked at it on MPC, and this is the elements that went up on the JPL, and it was because of this, it was possible to observe an occultation. And this was the solution that Shantanu, these project scientists at JPL, got for the astrometry, and this is what the solution would have been for MPC. So trying to see the shadow of a stellar occultation by this nucleus was impossible, because it was way away from where we thought it was. And Mike Kretlow predicted some of the occultations, and there were quite a few in December and January, and this was one of them. And successful observations were made. These are provisional profiles that will possibly be updated for publication. So I'm working with Mark Bowie, who has agreed that we can look at these. And there were two successful multi-chord observations. There was one in December the 19th and another in January 28th of this year. And this is basically the same object rotating. And the observations are in agreement with a very slow rotator. So there was one other postscript to this, and that was, how are we doing? Oh, right, great. I've almost finished. The other postscript is that there was a prediction of an occultation coming over the UK in May the 7th, and the weather forecast was dreadful. And we tried to get our people mobilized, and Nick was one of them. And in fact, 4 people were able to observe in difficult conditions, and 3 were unsuccessful. But Malcolm Jennings, who was further west, managed to get what's called a grazing occultation, and that's certainly the first time that's been done from the UK. In fact, I should add that no comet had ever been seen to occult a star prior to last year. And then in December and January, we managed 5 successful occultations. So, thanks to all of the work we're doing. So that's basically what I wanted to talk about. There is obviously a few pages on the website about Mission 29P, and I set up a group for people to discuss it, and so that's something which is quite active when the comet's visible. So thanks for listening.
you.